Lissajous figure. Okay, what is Lissajous figure? In the previous chapter, we had discussed the simple harmonic oscillators and estimation of their period and frequency. In this chapter, we will be studying the resultant of two simple harmonic motion acting on a particle in the same direction as well as in the perpendicular direction. Farmer gives the phenomenon of beats, while the latter the phenomenon of Lissajous figures. Both these phenomena are useful in physics in many applications. Lissajous figures produced by two simple harmonic motion may be mechanical or alternating voltage acting at right angles to each other. Okay. Resultant of two simple harmonic in the same direction. Resultant of two simple harmonic motion in the same direction. Same directions. Okay. Consider two simple harmonic waves of same period t. Consider two simple harmonic waves of same period t, capital T, same wavelength lambda. Let A and B be the amplitude of the two waves and phase difference phi. Let A and B be the amplitude of two waves okay, and phase difference phi, okay. The displacement of a particle at any instant t due to each wave is given by y1 equal to a sine 2 pi by lambda vt minus x. This is the equation number 1. And y2 equal to b sine 2 pi upon lambda vt minus x plus phi. Okay, this is the equation number 2. The displacement of a particle at any instant t due to each wave is given by y1 and y2, where v is the velocity of propagation of each wave. Where v is the velocity of propagation of each wave. Okay. The resultant displacement of the particle due to the superposition of the two waves displacement of the particle due to the superposition of the two waves. due to the superposition of two waves superposition of two waves is y equal to y1 plus y2, okay. Then y equal to a sine 2 pi by lambda vt minus x plus v sine 2 pi upon lambda vt minus x plus phi, vt minus x plus phi, okay, equal to a sine 2 pi by lambda vt minus x plus v common, okay. Then sine 2 pi by lambda vt minus x cos phi plus 2 pi by lambda vt minus x sin phi, okay. Sin a plus sin b, 2 sin a cos b plus 2 cos a sin b, okay. A sin 2 pi by lambda vt minus x plus b, then sin 2 pi by lambda vt minus x cos phi plus cos 2 pi by lambda vt minus x sin phi, okay. Then this is sin 2 pi by lambda vt minus x a plus b cos phi plus cos 2 pi by lambda vt minus x b sin phi. This is equation number 3. Then let a plus b cos phi equal to capital A cos phi and b sin phi equal to capital A sin phi, okay. This is equation number 4. This is equation number 5. Dividing 5 by 4. Dividing 5 by 4. We have tan phi equal to tan theta. We have tan theta, okay. We have cos theta sin theta, okay. We have tan theta equal to b sin theta upon a plus b cos phi sin phi upon a plus b cos phi. Squaring and adding 4 and 5, we have squaring and adding squaring and adding 4 and 5. We have capital A equal to under root of a square plus b square cos square phi plus 2ab cos phi plus b square sin square phi, okay. That is under root of a square plus b square plus 2ab cos phi, okay. Then the resulting displacement y from equation number 3 we have then the resulting displacement y from equation number 3 we have y equal to a cos theta sin 2 pi by lambda vt minus x plus a sin theta cos 2 pi by lambda vt minus x, that is a sin 2 pi by lambda vt minus x plus 5, vt minus x plus 5, okay? Hence, the resultant wave have the same time period. The resultant wave have the same time period, same wavelength and frequency, but has different amplitude and phase. Okay? Hence, the resultant wave have a same time period, same wavelength, and same frequency, but has different amplitude and phase, different amplitude and phase. Okay? Case first. Constructive interference. Case first, constructive interference, where y equal to 0, 2 pi, n 2 pi, etc. Okay? Tan theta equal to 0 and a equal to a plus b. Okay? The resultant vibration is in phase with component vibration. Okay? Is that the resultant vibration is in phase with the component vibration, okay? With the component vibration. Yes. Okay? Then, hence, if the phase difference between two waves is 0, if phi equal to 0, the reinforce each other. The reinforce each other if A equal to B, then capital A equal to small a plus b equal to 2a. Intensity of sound I equal to a square, that means 4a square. Therefore, the intensity of sound is maximum at those points where the two waves differ in phase by n to pi, or the path difference is n pi. Hence, n equal to 0, 1, 2, 3, this gives constructive interference. Therefore, the intensity of sound intensity of sound. Therefore, the intensity of sound is maximum at those points. Is maximum at those points. Maximum at those points where the two waves differ in phase by n 2 pi, or the path difference is n pi, or the path difference is n lambda. Here n equal to 0, 1, 2, 3, etc. This gives constructive interference. This gives constructive interference. Okay. Case second case. Case 2. Destructive interference. Where when phi equal to pi, 3 pi, 5 pi, 2n plus 1 pi, etc. Okay? If A equal to B, then capital A equal to 0, and intensity of sound I equal to A square, that is 0. Therefore, the intensity of sound is minimum. Therefore, the intensity of sound is minimum. Nearly 0, approx 0 at those points where the two waves differ in phase by 2n plus 1 pi, are the path difference 2n plus 1 lambda by 2. Here n equal to 0, 1, 2, etc. Okay? This gives destructive interference. This gives destructive interference, etc. Okay? Next is a condition for interference of sounds. Okay?